Thank you.
Yes.
Hi, nice to meet you. I'm Akihiro Inoue from the University of Tokyo. I'm an academic grad student of Professor Shinmine Shige, and unfortunately, he could not join this online meeting because of conflict with his schedule. But yes, just say congratulations here. And I would like to begin by expressing my warmest congratulations to Professor Shakura on reaching this remarkable uh, milestone of 80 years. And our works are based on your works, so I'd like to just, yes, congratulations, yes. And okay, so I very briefly introduce our numerical simulations of supercritical accretions onto the magnetized neutron star. Okay. Okay, so accretion disk is classified into three types depending on the accretion rate. For example, the accretion rate is around here. The geometrically thin and optically thick is formed as proposed by Shakura and Sanyaev in 1973. And our group has especially focused on the accretion regime. In this regime, in which the accretion rate is much greater than the Eddington value. And our group mainly investigated the supercritical accretion using the numerical simulations. For example, Osuga and Mineshige 2007 performed the radiation hydrodynamic simulations and showed that the supercritical accretion is possible. This numerical simulation assumed that the alpha viscosity for the angular momentum transport, as proposed by Shakura and Sanyaev. And this simulation also assumed that the Newtonian gravity. This radiation hydrodynamic simulation has subsequently evolved into general relativistic radiation MHD simulations like this, and they showed that powerful jets also appear around the rotation axis of the black holes. So today's talk focuses on the supercritical accretion onto a magnetized neutron star. Because the periodic X-ray pulsations are detected in some ultraluminous X-ray sources. These panels show the periodic X-ray pulsations, and the pulsations indicate that at least these ULXs are powered by the magnetized neutron star. So I briefly introduce our numerical estimations of supercritical accretions. Color shows the gas density and the radiation energy density. And this is a slice of the this is a results of the two-dimensional simulations. So we assume that the non-rotating neutron star and which has the dipole magnetic field, and we assume that its magnetic axis is aligned with the rotation axis of the disk. And the cyan lines represent the magnetic field lines. And the white vectors show the gas velocity vector for the region where the mass outflow rate is very high. And the white vector in the right panel shows the radiation energy flux vector for the region where the radiative luminosity is very high. This is the result of the numerical simulations. And after the simulation starts, gas accretes onto the neutron star due to the magnetorotational instability. And the accretion disk forms, geometrically and optically thick disk forms around here. And the powerful radiation and outflows driven by the radiation force appear above the disk surface. And the accretion columns appears around the magnetic poles of the neutron star. And also we can see that powerful radiation energy flux from the accretion columns forms around here. Yes, before closing my talk, again, I would like to say congratulations on reaching this wonderful milestone, your 18th birthday. Thank you.